Welcome to another walkthrough. This is the IAL M2 paper, June 2025, the most recent paper as of the time of recording. I'll try make sure I explain as simply as possible for each question, and I will give you a review after the whole walkthrough. Let's get going. Number 1. What do we have here? This is kinematics. So a particle moves along the x-axis at time t equals 0, p is at rest at the origin. At time t greater than 0, the acceleration of p in the positive x direction is that, right, where k is a positive constant. Given that t equals 1.5, the speed is 13.5, show that k equals 4. Well, this one, it gives you the acceleration, but asks you about the speed, which is the magnitude of velocity. So how about we find the velocity first? How to do that? Well, we integrate the acceleration, right? So velocity is the integral a dt. Now, of course, you're going to have to add the c constant after integrating, because if we don't put any limits yet, then there'll be a c constant. We're going to have that. Okay, so integral k 3 minus t squared dt. Yeah, so let's just put k out there. Integrating 3, we get 3t. Integrating t squared, we get t cubed over 3. Okay, and because we already know the bounds here at 0 and 1.5, right? But we also do have to add the c constant, and it has already told you that the speed at time equals 0 is 0 because the particle is at rest, right? So c constant is 0 basically. We don't have to add that, right? But I'm just writing here as well. So that is v, okay, at t equals 1.5. Yeah, so I'm just subbing in the 1.5 already there. Yeah, and we know that it is equal to 13.5, right? So here we're just going to solve the equation there. So 13.5 equals k, and then you sub all the bounds in. Obviously, if you sub 0 in, you get 0. So I'm just going to sub 1.5 in there. So 3 times 1.5 minus 1.5 to the power of 3 divided by 3. So k is equal to, well, if you solve the equation there, so it's just 13.5 divided by, what's that again? It's 3 times 1.5 minus 1.5 cubed, and then that divided by 3. Yeah, so k equals 4 there, yeah, as required. Just solving that. Okay, part A done. Part B. The displacement of p from O is s meters in the positive x direction. Show that that displacement is given by that expression, right? So we are just basically finding the displacement function, okay? And that is done by integrating the velocity function, and the velocity function is basically this guy, okay? So displacement equals integral 4 3t minus t cubed over 3, basically that, because we already got that. And because the 0 here is the velocity at t equals 0, so it's just 0. We don't need to add that in, and that's it. And after you integrate this, of course, you're going to have to put the initial condition as well, which is where the particle is at t equals 0, which is also 0 because it's at the origin at t equals 0. So if you integrate that, you should get there. So I'm just going to put 4 out, and in brackets here, 3t squared over 2 minus t to the 4 over 12, right? Just integrating that. That's just pure math there. And we plus 0 because, again, the initial condition there, okay? So if we simplify this, we should get the answer, hopefully. Seems like I need to pull out t squared, right? If I pull out t squared, and then 1 over 12 maybe. So I'm going to do, well, 4t squared, and then I have 3 over 2 in here, and minus t squared over 12 here first. Okay? And if I put 12 out, because I see that there is a 4 here, right? There is a 4 there. So that means if I want 1 over 3 as required there, I'm going to have to pull 12 out, right? So if I pull 12 out, what's left in the brackets, you got to work backwards. So if you pull 12 out, that's going to be like divide by 12 here, yeah? So it's going to be, 18. Because if you try, I mean, you can just try get some Q here from the required form, because we need 18 in there, right? So if you try pull 12 back in, yeah, if you try expand 12 back in, do you get 3 over 2? We do get 3 over 2, right? Because that's 18 over 12, yeah? And the other one is just t squared. And that simplifies to, of course, t over 3, 18 minus t squared, right? As required. Okay, so that's part B done. Part C, find the total distance that P moves before it returns to origin. Okay, so this one, if you want to work smartly here on this one, right, it's going to be quite risky to talk about just distance traveled. Because in fact, the S here that you got from part B is the displacement function, right? And displacement can be back and forth. So it can be negative, it can be positive. It's like if you go forward, it's going to be positive. But if you walk backwards, the displacement decreases, and sometimes might be a negative because you are walking backwards past the origin. So it could be negative. And that's tricky. But this is distance, right? So that means to get some idea, you probably need to plot velocity time graph. And the velocity time graph we got earlier, right, was this guy. Yeah? So, or we can take this guy, right? So that guy, so I'm just going to do Vt equals 4 3t minus t cubed over 3. Well, how about I take, just like I did before, right? Take 1 over 3 out as well. So 4 over 3, and also one of the t's there. So I get what? So I get 9 here, yeah, for the first term. And the other term will just be t squared. Yeah, so if you try expand back in, you're going to get, like the original form there. Okay? So the point here is to factorize and get a rough idea about the plot of the velocity function. So that is just 3 minus t times 3 plus t, right? Now this is a cubic plot. We just plot the critical values from these brackets. 1 is 0. Well, I probably have to stretch the left here. I mean, just the plot. Minus 3 and 3. Because this is not exactly a positive cubic, because you have 3 minus t there. That means there is a minus sign. So if I change this to minus, yeah, and they will all be t plus or minus something. We need to get to this form before we plot. And that means the plot will look something like this, right, rather than this. So it's going to look like this, where it's going to cut all of the critical points there, like that, roughly. Now we can ignore the left part here because this is time, so time is always a positive value, yeah? Okay, so what does it tell you here? It tells you that at t equals 3 here, the velocity starts being negative. Physically speaking, that's just when the particle starts to go backwards, right? Because if v is positive here, it's going to go to the positive x direction, right? Let's say go rightward. But if v is negative, it's going to go like that. So that means it's going to go forward for the first 3 seconds. And then in order to return to the origin, right? I mean, think about it. The area under the velocity time graph is the distance traveled, right? I mean, if you only take just one direction here, I mean, this is displacement, right? But it can also be thought of as a distance because you still go in one direction. But if you integrate over to this area, right? Because you're going to start walking backwards now, this area will cancel this area. So let's say if you go a little bit up to this point, yeah, this area will subtract from that area and displacement will be smaller. But in terms of distance, it's going to be greater. So you want this area, yeah, whatever it is, to cancel that positive area in order for it to return to the origin. So we are saying this area must be equal to this area. Now, what's the point? The total distance, right? You go forward to the turning point and then you go backwards the same distance. So let's say if you go, if this is 10, this should be 10. So the total distance is 20. Simple. So what do we do here? We just find this area and multiply by 2. Make sense? Yeah? So we drew this because we wanted to know what we're going to do. Because sometimes if you like just integrate blindly without thinking much about the graph here, it's going to be tricky. You might get it wrong. I mean, if there is no x-intercept here, you're going to be lucky. You will be fine. But in this case, probably not. So I'm saying that we're just going to get the displacement from 0 to 3. Yeah, putting the bounds in like that. Integral v dt, right? Or basically because we already got the velocity function there. Yeah, or we can use the, the displacement function. So we're just going to do 1 over 3, 3 to the power of 2, 18 minus 3 to the power of 2. Yeah? So that's 3 times, what's that? 18 minus 9, so that's 9, that's 27. So total distance equals 27 times 2, as discussed earlier, right? Meters. And that's it for the first question, right? Okay. Number 2. Just going to do it here. A particle P of mass 3 kilograms is moving on a smooth horizontal plane at time t seconds where 1 less than equal t less than equal 4. The position vector r meters of P relative to fixed origin is given by that. At the instant when t equals 4, P receives an impulse. 6I minus 3J Newton second. Find the speed of P immediately after the impulse is received, right? Okay, so impulse, if we work backwards here, so impulse is of course Ft, but I mean, you can also use the principal momentum, principle of impulse and momentum, saying that impulse is also the change in momentum. I mean, by definition, impulse is force times duration of impact. Impact force times duration of impact. That's by definition in physics. But impulse is equal to the change in momentum. That is the principle, right? Because impulse causes a change in momentum, right? So impulse is then mv minus u, where v is the final velocity and u is the initial velocity, mass m, and I is the impulse. So we received the impulse of 6I minus 3J. We already know what the impulse is. We already know what the mass is. What about the final speed and the initial speed, right? So the speed or the velocity here should be obtained from the information in the question. And the only information that might be relevant to velocity here is the vector r. Because if we differentiate r, we get the velocity. Whoops, I dropped my pen. Sorry. If we differentiate r, we get the velocity, right, guys? Never mind. Okay, so I'm just going to do velocity vector v equals dr by dt. Yeah? So we're going to differentiate this guy right here. And separately, for I and j, right, because this is vector. So differentiating t to the half, we get half times 4, that's 2, and then power minus 1, we get that. Yeah, and then this is I and minus 3j, because that's the derivative of 3t. Okay, so because now it receives the impulse at t equals 4, so if we plug 4 in, let's say velocity at t equals 4 here, we're going to get t 4 to the power, well, 4 to the t to the power of minus half is basically 1 over square root t, right? So it's just that, yeah, I minus 3j. So that's basically I minus 3j because it's 2 over 2 there. Now this is the velocity at time equals 4, and that is just before it gets the impulse. And we call this the initial velocity before the impulse, right? So it's going to be plugged into this guy. And we're good now because we're going to get v there. So if I just plug in everything here, so impulse 6I minus 3j equals m is 3 kilograms, v minus u, which is I minus 3j. So if you solve this vector equation, you're going to get the velocity, right? So if I divide by 3 both sides, I get 2I minus j there equals v minus I minus 3j. So if you add I minus 3j on both sides, so I'm going to get I 2I minus j plus I minus 3j equals v. So v equals 3I minus 4j, right? Meter per second. But don't forget, I think it asks the speed, yeah? So the speed would be the magnitude of velocity. So we are doing the Pythagoras there. So we get 5 meters per second. Okay, so that's fine, yeah? Well, just for safety there, I'm just going to put 5.0, yeah, 2 sig figs there, just for the sake of significant figures. Okay, number 3. Wow, center of mass. Okay, a uniform rigid wire framework shown in figure 1 consists of 2 wire semicircular arcs A, B, C, D, both with center. Yeah, you can read the question too. And then part A asks you show that the center of mass of the framework is a distance that from AB. Okay, so usually we do this by a table, right? So we're going to do a table. Okay, table. And, whoops. So the column will be for separate shapes, right? So I have a leftward semicircular here and a rightward bigger semicircular. Oh, actually, this is wire framework, so I should split into small wires like that. It's not a lamina. So a bigger wire there. And don't forget we have 2 of the vertical wires, and they don't account for, so the center of mass of the vertical wire here would be just at 0, right? Because we are talking about the distance left or right from the origin, because it says the distance from AB, right? So this is the distance here. So if you go back to the diagram, yeah. So where is the center of mass? Is it here or where? So, but we know that the straight wires here, they have the center of mass at this and this, which is aligned with the origin. Okay. So when we tabulate here, we have to put the length, right? Because the length will be the major contribution to the mass of the wire. Because when we find center of mass, x bar, it's going to be sigma xm over sigma m. But because this is a wire framework, so we assume that they have uniform mass per length, mass per unit length, right? So all of them have the same mass per unit length. That is why we can like simplify this to just the length rather than the mass. Yeah, that's just the way it is for uniform wire framework. So we should get an L and an X, right? X bar for each shape as well. So we can get X bar combined of the whole shape. So the length of the leftward semicircular there is just, well, the radius is what? A, right? Here is A, yeah? Radius of CD is A. So it's just 2 pi r over 2, that's pi r, so just pi A, right? That's just pi A. And this one is just pi 2a, yeah? So 2 pi a for the bigger one. And these two Well, I'm going to multiply by 2, so together all of them is 2a, right? Now the x bar of the smaller semicircular, well, we're given here that the center of mass of a semicircular arc of a radius r is 2r over pi from the center, so it's around here for the left one. Yeah, so but it's exactly 2r over pi, so it's 2a over pi for the smaller one, and the longer one is 2 times 2a, which is 4a over pi. But if we do negative for the left and positive for the right, this should be a negative. Yeah, because we want to find rightward where the location of the center of mass to the right from the origin. I mean, it could be to the left in some cases, but conventionally we just do right positive here. And again, as mentioned before, the center of mass of the vertical wires here are just 0, right? Because we measure from the origin left or right. So that's just 0 there. Okay, so this will just be equal to, if you multiply and sum the subtotals up, so we have pi a times minus 2a over pi plus 2 pi a times 4a over pi plus 2a times 0. And of course, we have to add up all the length as well to divide here. Yeah, so it's going to be pi a plus 2 pi a plus 2a, right? Okay, that's it. If you simplify all this, you're going to get hopefully what is required there in part A. Okay, so the top bit is just, this is pi, cancel pi, so you have minus 2a squared here, and then you have 8a squared. Yeah, so minus 2a squared plus 8a squared is 6a squared on top, right? And then divided by, well, the bottom you get 3 pi a plus 2a. That kind of, yeah, that looks fine. 1a cancel, and then you can factorize. No, you don't have to factorize anything, just 6a and then 1a cancel that, so it's 3 pi plus 2 from AB. That's it, as required, right? That's part A done. Part B. The point E is on the arc AB, yeah, point E here. And the angle AOE is a right angle. Okay. All right. The framework is freely suspended from A, yeah. The framework hangs at rest in vertical plane where AE makes an angle theta. Okay. So let's draw AE first here, just AE, yeah. So that's A, that's E. And then let's say O is here as well. So I haven't tilted my shape yet, yeah. But the downward vertical will pass the center of mass here. Let's call that CG. Okay. So the downward vertical will be this. It's going to be the line that is vertical when you hang it, when you actually hang the shape. The angle theta here is the angle between AE and the downward vertical. So it's this angle. Okay. It's going to be tricky here. It's not easy to find, because usually what is easier to find is this angle. You already know this side, you already know this. This is just this distance, right? So this distance here is this distance, right? I'm just going to color code that. Well, the vertical there, right? The vertical is just this length, right? So, and this is A, and this is also A. So that makes 2A for this vertical side. Okay. Let's try find this angle first then. I'm going to call it alpha maybe. So tan alpha is going to be equal to, well, SOHCAHTOA, opposite over adjacent. So that's 6A over 3 pi plus 2, all divided by, yeah, 2a. All right. So if you cancel the 2a with the 3a, you get 3 with the 6a, sorry, you get 3a over 3 pi plus 2. So if the question only asks for this, then this question would have been just 2 marks. But it's 5 actually, so there's something more to it. because we need to find theta, not alpha. Now, how do we find theta? Well, how about, yeah, so you can find maybe this angle first. Now note that the question asks the exact value of tan theta. It doesn't actually ask you what theta is. Yeah, I didn't mention that, sorry. So let's find this yellow angle. Let's call it beta first, yeah. And we can try find tan beta, right? So tan beta is what? Opposite over adjacent. So opposite here, this is OE. And OE is obviously 2A from the diagram there. So that's 2A divided by also 2A. So that's just 1. Now, of course, tan theta is not going to be tan beta minus tan alpha. That's not right. But we know that tan theta is going to be tan, in brackets, beta minus alpha, like this. So it's not tan beta minus tan alpha, but it is tan, in brackets, beta minus alpha. Different. Now, how are we going to get a crack on the right-hand side there? Because we want tan theta, of course. And the question specifically asks for exact value. So you can't just solve for the angle and hope that you're going to get exact value for tan theta. It's not going to be that simple. So we do this by using pure math knowledge. Additional formula for tan theta. Tan A minus B, yeah? So we know that tan A minus B, in this case, beta minus alpha, is going to be 1 minus, wait, hang on, no. It's tan beta minus tan alpha, yeah, if you look at the formula sheet. I just happen to remember. That's 1 minus tan beta tan alpha. And if you plug everything in there and simplify the thing, you're going to get there, right? So that's the hard part. It's just for you to recognize that you can use this. So tan beta, we already found 1. Tan alpha is just the whole thing there. Yeah, we got everything we need. We got the recipes here. And, oh, hang on. Oh yeah, that's right. And this is 1 minus tan beta is still 1, and then tan alpha was still 3a over 3 pi plus 2, like that. If you make the denominators the same for top and bottom there, you're going to get 3 pi plus 2 minus 3a, yeah, all divided by 3 pi plus 2, and this is a big fraction, and then that's going to be 3 pi plus 2 minus 3a. Wait, why do I get the same thing here? Hang on, is something wrong? Oh, sorry, this must be a positive, yeah, because otherwise they will cancel that. Yeah, this must be a positive, sorry. Okay, there you go. Yeah, I think that's fine. It feels a bit weird though, hang on. 1, yeah, okay. So the denominator of the denominator here is also 3 pi plus 2, which cancel these. Yeah. Okay. So, wait, let me check something, I think. 6a. Oh, sorry. I forgot to cancel a here. Yeah. So that must be 3. Okay. Just 3 there. All right. Yep. Okay, I think that's it. Let me double check everything. Okay, yeah, that's fine. So that simplifies to 3 pi minus 1 over 3 pi plus 5, right? Okay. Yep. So that's it. That's the tan theta that they want. Okay. And that question is done. Next, number 4. A rough plane is inclined to the horizontal at an angle alpha, where sine alpha is 1 over 7. A car of mass 750 kilograms moves up a line of greater slope of the plane. The total resistance to the motion of the car from non-gravitational forces 200. The engine of the car is working at a constant rate of 20 kilowatts. A, find the constant speed in meters per second. Right. Constant speed means that the resultant force up the slope or down the slope, doesn't matter, is 0. So let's say this is the slope and that's alpha. So a car is moving up, yeah. Okay, and constant speed v. So sigma f equals 0. That means you're going to have the force, the engine force is power over speed, right? You need to know that. And we have the 200, which is the non-gravitational resistive force, and also the weight component, of course, which is the gravitational resistive force, and that is usually mg sine alpha, right? So we're going to equate P, which is constant at 20,000 kilowatts, over V equals 200 plus the mg sine alpha, and m is 700. I'm going to plug everything in now. 750 times g, 9.8, times sine alpha is 1 over 7. Okay, so if you solve for the v, you should get the answer there. So I'm just going to already plug everything in the calculator. So 200 plus 750 times 9.8 times 1 over 7 there. So that's the right part. And, oh, hang on. I got to swap that because when you make v the subject, you're going to have 20,000 here on top instead. Okay. Times 1 over 7. Yep, that's 16 meters per second. Okay, so that's the speed. Part A is done. Part B. Find the acceleration of the car at the instant when it is moving up the slope at 10 meters per second. Now, note that the speed decreases quite a lot. That means there is now a greater force. Because if you look at the equation here, when you have a smaller v, you have a greater force. Inversely proportional. So there will be a resultant force up the slope, and that's why it's asking for acceleration. Just understand the physics there first. So we're going to have to use now sigma f equals ma. Just the Newton's second law there. So the sigma f, yeah, the upward minus the downward, so 20,000 divided by 10, that's the engine force upward. Minus 200 is kept the same. And then the weight component, 750 times 9.8 times 1 over 7, because that's the sine alpha, is going to be equal to m, which is 750 times a. So if we solve for a, we're going to be home free here. That's easy. So just plug everything in again. So that's 2,000 for the force minus, well, let me do fraction. 2,000 minus 200. And then minus the weight component, 750 times 9.8 times 1 over 7. Yeah, still the same thing there from before. And then divided by 750. Okay, so acceleration is 1. I'm just going to make it two significant figures there. Okay, is that right? Let me just check. Okay, yeah, should be. 1 meters per second squared. Okay, that's the acceleration when it's moving up at the speed 10. Part C. At this instant, which is the speed 10 presumably, the car is at point A and the engine of the car is switched off. The total resistance to the motion of the car from non-gravitational force remains constant. Using work energy principle, C, find how far up the slope from A the car would travel before coming to rest. Well, you go from having a speed of 10 to having no speed at all. You are losing kinetic energy, right? And when you go up, this is the height increase, right? Delta H. But this is the distance you move up the slope, like the incline distance if you like. And there is a relation between those two distances. Yeah, now why am I talking about this? Because, okay, let's talk about the big picture. Work energy principle. So the energy lost usually is going to be equal to, because you are transferring from some energy to some other energy. So I'm doing energy loss equals energy gained, but plus some work done to overcome friction or resistive force. The energy loss in this case is the kinetic energy lost. The energy gain in this case is the GPE, gained. The work done to overcome friction is just basically the resistive force times the distance. So it's just F times D. And F being the 200. Yeah. So if you find a change in kinetic energy from 10 meters per second to 0, we're going to have 1/2 m and v squared minus 0 squared, like that, because it's just, from 10 to 0, equals the GPE gain, which is the change in height, right? So m g h, well, because we want to find how far up the slope, we want to find d, so we should make h in terms of d. That's better, because we don't want to make too many variables there. Now delta h here is just d sine theta, right? If you do the trigonometry there. And sine alpha is again 1/7, so I'm just going to do d/7 here. Yeah. Plus, again, force is 200. That's the resistive force, the non-gravitational resistive force. And d is kept the same as d. Okay? So if you solve this, you get d. And I'm just going to do like d equals. So if I, do the left-hand side, so I make d the subject here, all divided by, well, you gotta simplify this right-hand side first. If I extract or factorize d out, and then I'm gonna divide the coefficient of d to the other side, that's why I'm writing the denominator here. So it's 750 times 9.8 times 1/7 again, plus 200. If you solve that, you get the answer for d, yeah? So 1/2 times 750 times 10 squared divided by 750 times 9.8 times 1/7, and then plus 200. Yeah, so that's 30 meters. Just checking everything here. That should be fine. Yep. Okay, and that's it. That's done for question 4. Next, question 5. A particle P of mass 2m and particle Q of mass m are at rest on a smooth horizontal plane. Particle P is projected with a speed u along the plane towards Q, and particles collide. The coefficient of restitution between the particles is E, where E is greater than 0. Part A, show that the speed q after the collision is that. Right. Okay. So basically in M2, in collision, we have momentum conservation and coefficient of restitution. Okay, so let's draw some diagram first. We have particle P of mass 2m, initial speed. Let's say we're going to convent that rightward is positive direction u. Okay, because particle P is going to move to collide with Q here, Q mass m, and initially it is at 0. It is at rest, right? So the coefficient of restitution, E. Okay, I'm gonna color code red being the velocity after the collision, right? So the velocity after collision, let's say they both go to the right, and this is VP and this is VQ, because they don't tell you anything about after the collision, so we gotta make up something here first. Now I convented it to be positive because when you do relative speed, it's easier. Why do I need to care about the relative speeds? Well, because we are finding the coefficient of restitution. The coefficient of restitution is calculated by the relative speed of separation divided by the relative speed of approach. Well, the approach one is easier because it's the one before. Because this is 0, this is u, so relative speed is u. We gotta make the relative speed positive, yeah? And the relative speed of separation, well, because presumably they both go to the right, And the only way it makes sense is for Q to be faster than P. Otherwise, P will kind of like, be skidding or be, at the back of Q all the time, which is not possible. Q has to be faster, right, for them to be separated. So we do VQ minus VP here. And that's the relative speed. Because if they both go to the right, the extent by which speed of Q is greater than the speed of P will be the relative speed. Okay, so that's why I have that equation. Well, let's keep it there for the time being. And again, this is one part done, and then let's do conservation of linear momentum. Okay, so total initial momentum before collision is just 2m times u plus 0. Just going to write as well because there's no momentum for Q before collision. Equals, so this is going to be 2mvp plus mvq, right? Like that. So if we cancel the m, we have 2u equals 2vp plus vq. Well, seems like we have simultaneous here, yeah? So from this equation, if I say make vq the subject, now let's make vp the subject because we want to find the speed of q here, so we shouldn't eliminate q, so we're going to make vp the subject. So vp equals vq minus eu, isn't it? Let me double check that. Yep, vq minus eu. Okay, so we're going to sub that in here. 2 vq minus eu plus vq. If we solve for vq here, we should get the answer, right? So expand in, we get 2 vq minus 2 eu plus vq. Collecting all the term and moving 2 eu to the left, I get 2 and then u plus, well, let's factorize 2u out, and then I have, 1 plus e, and then divided by the 3 from the 3vq, so I get that. And that's it. Yeah, this is algebraically correct. Okay, so part A is done. Part B, the total loss of kinetic energy due to the collision is that, where k is a constant, b find the value of k. So the total loss in kinetic energy, you need to find kinetic energy before and after collision and subtract them, right? Yeah. So delta KE is going to be equal to, well, the one before collision should be greater because you lose kinetic energy. And it was from the particle P alone. So half m v squared. Yeah, like that. Minus half, now we got to sum up, right? We got to sum up the kinetic energies from both particles. So it's going to be half 2m vp squared and minus again half mvq squared. Yeah, just to set up the equation here, and we're going to plug in all the variables, right? And we set this to k 1 minus e squared mu squared because they told you that the loss of kinetic energy is that. Yeah? So we're going to have mu squared here for the first term, and then minus vp squared. What is vp? Vp is vq minus eu, but vq is that, right? So let's find vp here first. I'm just going to move down here so that I can find vp to plug in here, yeah? So vp is vq minus eu. That is, so if we consider this and minus eu, so basically you're going to have one less eu there. So this was 2u plus 2eu, right? So you're going to have 2u plus eu, yeah? Right? And then, no, hang on, that's not right. Let me just write everything. So 2u over 3 plus 2eu over 3 minus eu. Yeah, that should be the VP. All right. Well, if we do in a third, right? So that's going to be 3 over 3 there. So that's minus EU over 3 instead. So if we simplify that, we are going to get 1/3 u again, and inside there we have 1. This will become what? -1, right? Yeah, so minus e, like that. Yeah, minus 1/3 ue instead. Okay, so that's for the VP. And then we put it in here in the kinetic energy formula. Because I already canceled the 2 here, I only have m there. So this is 1/3 u 1 minus e all squared. And then the last one is VQ. We already got that, which was, of course, 2u/3 1 plus e squared. So if we simplify all this, we should solve for k. Yeah, we should be able to solve for k. Now, the m cancel, of course, I think. Yeah. And then we got to be careful here. Well, if you try c through here, you have u squared in all the terms. So if you expand the u in here, you get the u. If you expand the 2 in here, you get the u. So u squared will also cancel. I'm just going to write k times 1 minus e squared equals. So if you cancel the u squared, you get 1 there. If you cancel the u squared and then simplify this, you get 1/9, 1 minus e squared, like that, right? And for that one is 1/2, well, 1/2. And then 4/9, u squared cancel. Now I only have 1 plus e squared. Okay, just simplify bit by bit. Don't rush. Easy does it. Okay, well, how about I multiply everything by, well, you see you have 2 here also canceling with 4 there. How about if I multiply everything by 9, all the terms? So I get 9k, 1 minus e squared there, equals, so 9 also have to multiply 1 there, and 9 will cancel that. And I'm going to expand 1 minus 2e plus e squared here as well. 9 also cancel with that. We have 2, and then 1 plus 2e plus e squared for this one as well. Okay, so we are almost there. So 9k, 1 minus e squared equals 9. I'm just going to expand now. Minus 1 plus 2e minus e squared. Minus 2 minus 4e minus 2e squared. Okay? And k should just be making it the subject. Now simplify the right hand side. So that becomes a 6, right? The number. And the e becomes a minus 2e. And the e squared becomes 3e squared. Over 9, 1 minus e squared. Okay. Right. I'm just going to double check this first. See if I got everything right. Okay. I mean, that doesn't look right to me. Maybe I made a mistake somewhere. Let me find out. Because I mean, I'm having a doubt that it should simplify to just a number, right? But it doesn't here. So I'm just gonna maybe take a look. Take a look first. Well, we got that right. We got that one right. 4/9, 2/9. I'm going to check the VP again. So VP was VQ minus EU. That should be right. Wait, no. It's 2, isn't it? This is 2, definitely. Okay, I found it. There you go. The VP was wrong. Wait, hang on. And I almost changed the wrong one. So this is the VP. This is the VP. Okay. So everything else remain the same, but inside here I should instead get 4 minus 4e plus e squared. Okay, so that should be 4, 4, 4, 4, and e squared. Alright, is that? Yeah, now we get some cancellation. 4e goes away. And then I have here 3 minus 3e squared. And because that is just 3, 1 minus e squared divided by 9, 1 minus e squared. So that should simplify to 1 over 3. There you go. Okay. So that's it for the part B. Part C. The magnitude of impulse of Q on P in the collision is 8 mu over 9. Find the value of E. Okay. So the value of E, okay, impulse is mv minus u again. Because this is impulse of Q on P, we're going to have to find the mass of P, which is 2m, speed of P, yeah. So VQ minus U, sorry, VP minus UP. Final speed of P was again VP, we got it here, 1 over 3U 2 minus E. 1 over 3u 2 minus e, yeah. Minus u was just u, right? Because the initial speed before the impulse was just u for particle p. And the impulse here has the magnitude of 8 mu over 9. Because this is about magnitude, so we might get a negative sign here, but we're going to make it positive, right? Just by doing a modulus here. Okay? So if you simplify in here, you get 2m, and what is that? So this is basically 2/3 u minus u, so you get minus u over 3 first, and then if you expand this in, you get minus ue over 3 as well, right? Yeah. So the m cancel, yeah. And I have here 8u over 9 equals, if I pull u out, I get 2u. And that's going to be an over 3 out as well. And minus out here, yeah, still modulus sign. That's going to be 1 over just 1 plus e, right? Yeah? Just 1 plus e there. Because I factorize u over 3 out. Minus u over 3. Okay, and you can cancel the u here. You can cancel the 3, I get 3 here. Cancel the 2, I get 4 here. So that is saying 4 over 3 equals, now we're going to take the minus out because that's absolute, 1 plus e. That means e equals 4 over 3 minus 1 equals 1 over 3, right? There you go. Okay, so that's part C done. Part D. After the collision, Q goes on to hit the vertical wall, which is fixed at right angles to the direction of motion of Q. The coefficient of restitution between Q and the wall is F. After Q has hit the wall, Q has the same speed as P. Alright, so Q is definitely going to the right now with the speed VQ before hitting the wall. And we already know the E, so we can calculate VQ. So VQ, yeah, was again given in A. We already found it. So if E is a third here, so that's going to be 4 over 3, right? So 4 over 3 times times 2, it's going to be 8 over 3. 8 over 3 divided by 3, that's going to be 8 over 9u, right? Yep. And then because we are given the coefficient of restitution, so after colliding with the wall, it is just simply F multiplied with this. So the speed after hitting the wall would just be F times the initial speed before hitting the wall. Okay? And it is saying that this speed is equal to the speed of P after the first collision with the Q, which is what? VP was, we found it to be, wasn't it this guy? Yeah, it's it's this guy right here. It's 2 over u over 3. Yeah, it's the same as that. So it's 1/3 u2 minus e, and e is again 1 over 3. So if you subtract that, you're gonna get 1 over 3 u. 2 minus 1 over 3 is gonna be 5 over 3, right? Yep. Equals f 8 over 9 u. U cancel. Yeah, and 2 of the 3's here cancel with the 9. So f is just 5 over 8. That's it. That's the value we want, right, for part D. Okay. Next, question 6. All right. A uniform rod AB of mass m and length 2a has its NA on a rough horizontal floor. Okay. A smooth horizontal rail is fixed above the floor. The rod rests in equilibrium against the rail at point C, okay, point C here, where AC is 1.5. The vertical plane of the rod is at the right angle to the rail. The rod is inclined to the floor at an angle theta here, as shown in figure 2. The magnitude of the normal reaction exerted on the rod at C is S. All right, so I'm just going to quickly draw the diagram here. So we have a rod, and then as at the rail here, and then we have a normal reaction S, yeah, and at NA here, and the angle is theta here. Okay, so that is 1.5 A, and because the rod is 2A in length, so this is 0.5 A. And then we need to show at A, show that S is blah blah blah. All right, so when you do equilibrium, yeah, usually, I mean, from my experience, it's gonna start with moments, right? This is just finding one force, yeah, which is S. Now, if you think about it, you have other forces here. You have the normal N here, yeah, I make it N, and you also have friction here because the ground is rough. It's a rough, let's say somewhere, I think rough horizontal floor. There you go. Yeah, so you should have also friction. Now, I mean, in this case, friction is going to the right because you would have the S component going to the left there, just to balance them out, yeah? Now, because you have these two forces as well, and you don't know them yet, I mean, taking moments about A would be a wise choice to do here first, in order to find S. So if we take moments about A, yeah, we do a moment equilibrium about A. So the only two forces we should consider should just be, yeah, S is one of them, of course, and the other one is just the weight of the rod. Because the mass of the rod is M, so the weight is mg. So we know that the rod is uniform, so that means that length there is going to be just A. Yeah? So if we do mg times this perpendicular distance, so I prefer not doing anything with the force, but resolve the distance here. So this distance is just A cos theta, because you're going, close to the angle. Close is cos there. So this is A cos theta, and this is mg. So it's mg times A cos theta equals, and the other moment, like mg A cos theta here is the clockwise moment. The anti-clockwise moment is from S, right? So we do S times 1.5 A, right? I forgot A, yeah. So that's it. That's the anti-clockwise moment. And then if you simplify this, you cancel A, and then you're going to get S as, if you divide 1.5 on both sides, yeah, you get mg cos theta and 1 over 1.5 there. But 1 over 1.5 is 1 over 3 over 2, which is 2 over 3. Yeah, it's just, they just want it as a simplified form like that. Yeah, so we show that, yeah. Part B. The magnitude of the vertical component of the force exerted on the rod at A is V. Okay, yeah, so it wasn't N then. I just have to change the letter here to V, right? Vertical component of force exerted on the rod at A. Yeah, A is the ground here. And we want to prove that V is that. So now we have used the moment it is probably wiser, again, that we now use either force on the y-axis or on the x-axis. Yeah, either solving the equilibrium for the vertical or horizontal forces. Now here V is the vertical, so we should do something about the vertical then, right? So I'm just going to solve the force vertical, which should be 0 because this is static equilibrium. So that means our vertical forces, yeah, we have V, we have mg, and the other one is the component of S, right? But before we find the component, we should know maybe this angle first. Well, is it actually theta here? I just draw a random letter there, but it could be or it couldn't be. So let's find out. If this is theta, so that is also theta, right? Because this is alternate angle. Well, because this is 90 degrees, right? So this must be 90 minus theta. Okay? Well, this is also 90 degrees, right? This one. I hope you see the animation there. That makes this 90 minus, in brackets, 90 minus theta, which makes it theta. Okay, so I'm just proving that that is theta there. Okay, so that's fine. Then, so the vertical component of S there would just be S cos theta. Okay, so we have V plus S cos theta equals mg. That's just the vertical force balance, right? Okay, so V is just mg minus S is just 2 over 3 mg cos theta. Okay, and then cos theta again. So that is why we have cos theta squared here, yeah, in the question. Okay, so we're going to simplify that. Well, if I take mg over 3 out, right? So yeah, just what they want there, mg over 3 outside. So this term will be left with 3, right? Because if you try multiply this back in, you get mg. That's just the way I go with it. I mean, I'm not thinking about if you factor this out, what will be left with so the way I figure this out is just multiplying back to see, because they even show you here what should be left inside. So you just try inspect backwards, see if you multiply mg over 3 inside, yeah, like in this case, do you get what you have here? Just to verify your algebra there, right? It's easier. And then, well, if I take mg over 3 out, that's going to be left with 2 and then cos squared, right? Inside the brackets there, which is what they want there. So this is as required. Easy, yeah? Next part, given that the rod is in limiting equilibrium, very important keyword here, and the coefficient of friction between the rod and the floor is 4 over 7. Well, limiting equilibrium means that we can take the friction as mu times the normal reaction. I mean, if for those of you who think that it's always this equation, then it's wrong. It's only at limiting equilibrium. So this is maximum static friction. If the system is moving, if the object is moving, then yeah, it's mu n. It's always mu n when it's dynamic friction. But this is static friction here. It is maximum when the object is about to move, and we call that limiting equilibrium. All right. So if it's not limiting equilibrium, then friction will be less than this value. Okay. So friction is then 4 over 7 times V, because V is the normal reaction in that case. So basically, you know, in static equilibrium, you have used moment. In this case, you have used moment, you have used vertical force. There's only one option left, horizontal force, right? Horizontal force balance. So you're going to do F, which is the friction here, equals the horizontal component of the S. So that would be F, which is 4 over 7 times the whole V there. Yeah, I'm just going to copy those down. That's the friction, and must be equal to the horizontal component of the S, which is S sine theta. So S is 2 over 3 mg cos theta. This is just the S. And we multiply that by sine theta, right? Okay, to find the horizontal component. Obviously, mg cancels. Yeah. Okay, fine. And then I also cancel 3 here and here as well, algebraically speaking. So I'm going to be left with what? Okay, we want it to be 10 squared. All right. Okay, let me expand everything first. So I'm going to get 12 over 7 here minus 8 over 7 cos squared, right? Just expanding all that to the left. And to the right here, I have 2 sine theta cos theta. Well, those of you who have done P3, of course, you see that this is double angle, but is there a point there? No. We want to make it tan, and there's no double angle there. So how do we make this equation tan? Well, we can manipulate. Well, how about we divide by something? At least if you divide this by cos squared, this is going to turn to 1. And that's going to turn to tan, right? So if you divide this by cos squared, it's going to cancel 1s here, and this cos and that sine will make a tan, right? So how about we do that? Divide by cos squared. So, I mean, if you divide the first term by cos squared theta, then it's going to be 1 over cos squared theta, multiplying that, 12 over 7. So that's sec squared, right? Yeah. So this is 12 over 7 sec squared theta minus, well, that will cancel out to 7 over 8 over 7. And this, as we discussed, it was tan theta there. Well, how about I multiply out by 7, yeah? So I get 12. Well, again, sec squared, isn't it 1 plus tan? Yeah. So this is 1 plus, I'm just going to do tan squared plus 1. Yeah? It's identity, right? And we also multiply by 7 here, don't forget, so minus 8 there, and multiplying that by 7, we get 14 tan theta as well. All right, so far so good. Yeah, we're almost there. So if we expand 12, we get 12 tan squared theta. Well, if I move the 14 tan here to the left side, I get that. And then the number term, which is 12 minus 8, so it's plus 4 there. There you go. Yeah, everything is fine. Well, obviously, we can simplify that to 7 tan squared minus, that's not 7, that's 6, yeah. And 7 tan theta here plus 2 equals 0. I think that should be it, yeah. P, Q, R are integers, yeah. We got them to be integers there. So that's it for number 6. Number 7, part A. We have projectile here. A small stone is projected from point O on a horizontal ground. The stone is projected with speed 20 meters per second at an angle alpha to the ground. When the stone is 11 meters above the ground, the vertical velocity component stone has a magnitude v. Okay, so we have some trajectory. And by the looks of the diagram, it's going to hit some plane here. But we are interested at when it's in the air. We don't know where that is, but the only thing we know is it's 11 meters above the ground. So it's projected here, and then it flies to 11 meters there. Okay, so projected there with the speed of 20 meters per second. And then at the point here, at this point, we are told that the magnitude of vertical velocity is v. So I don't know about whether it's going up or down. Let's say because I drew it like this, so I'm going to make it going down. It doesn't really matter because it's speed. Because in the first part here, A, we have to show that v equals 6 using the model and the principle of conservation of mechanical energy. Mechanical energy, basically you have kinetic energy, gravitational potential energy, elastic potential energy, and some kind of work done to overcome friction or resistive force. That's it. That's all there are. Okay. So we're gonna consider these, but of course this is a rigid body, so there's no spring effect here whatsoever. So you're gonna ignore EPE, right? Just KE, GPE, and work done to overcome friction. Now consider from the starting point, point O, and somewhere in the air there, we have speed of 20. So what do you think is going to happen to this energy? What energy is this? Kinetic, right? Because you have a speed, a moving particle. And then it flies higher, defying gravity. So you are gaining GPE when you go higher, right? So here, obviously, GPE will increase. But here, if we reference this as GPE equals 0, yeah, which is possible. Then we are gaining GPE, but we are losing KE. Okay, again, using input and using gain and loss here, we're gonna have KE lost equals GPE gain, yeah, plus work done overcome friction. But of course, in this question, I think that this is assuming no air resistance. Usually it assumes that, but it doesn't say here. We can assume, because in the air, there's only air. There's no friction on the ground there. So we assume this is 0. So it's just KE loss equals GPE gained. KE loss, right, it's just half. M, well, we don't need to know that. We just say M. Well, loss, right, so it's from 20 there. This one should be greater kinetic energy here. Yeah, so we're going to do 20 squared minus. Now, how do we deal with the point here where we don't know much about anything, but we know that each component is V and 2V respectively? Well, we can separately calculate the vertical and horizontal components. So, for example, the horizontal component would be half M and then 2V squared like that. And this one will be half M and then V squared. So if you add them up, you can still factorize these out. I only have like 2V squared here, which is 4V squared, and this is V squared, right? So we're going to minus 4V squared and also minus V squared. I mean, it's like just adding them up and just put them to subtract the initial kinetic energy there, basically. Yeah, so we can separately calculate the kinetic energy of the two components. So that's just the left-hand side done. Equals GPE gain. So it's M and G, which is, this question assumed to be 10, huh? Okay, so M times 10 and then times 11. That's it. That's the GPE gain. So we solve for V. Note that M cancels here, yeah? All right. So what is that? It's, so we have here, we move 2 to the other side, and here we simplify 400 minus 5V squared equals, that's 220, right? Yep. So 5V squared equals 180. So V squared equals 36. So V equals 6. Plus minus 6, but we talk about speed here, so it should be 6 as required, right? So that's part A done. Part B. Figure 3 shows a plane fixed to the ground at an angle 60, yeah? The stone hits the plane at point A, yeah? Now it's going to hit the plane. The direction of the motion of the stone is perpendicular to the plane at the instant stone hits A. So it is basically saying that when the stone hits the plane here, the resultant velocity is into that direction. Okay, so that's velocity. Okay, we want to find the height of A above the ground. So basically we want to find this. Let's say that is the ground then. Okay, we want to find H here. Two significant figures, knowing that this is 60 degrees. Okay, now again, this question doesn't tell you what to use or how to do. You can use kinematics, you can use Suvat, but it's going to be a little tricky. But I would like to use energy again for this one, because you can use like the exact same approach. You just find a different unknown here. You are starting with the 20 meters per second. You are losing kinetic energy, gaining GPE. So at this point, you have GPE, and it's just mg and this h. And then you have kinetic energy here, you have some speed here. Let's get some more idea about the speed when it hits the plane. So if this is the speed, right? Now if we resolve that to vertical and horizontal like this, it must be going down, right? Because in the diagram it's like it's going down like that. And then what is 60? So 60 is here. So isn't that also this angle? So this angle here. So that would be also, hang on, let me just draw that properly. So this is 60. This would be 30, right? Because this is 90 degrees, right? Because the question tells you that this is 90 degrees. Yeah, you can see the effect there. This is also 60 then. All right, so that's it. So this is 60. Yeah, let me try that again. So this is 60, this is 30, this is 60. Yeah, okay. All right. So that means the vertical component downward here is V cos 60, and this one is V sine 60, right? Okay. Well, but don't forget, because we assume no air resistance, that means the horizontal component remains constant. Yeah? So the horizontal component V sine 60 here is going to have to be, well, don't confuse between this V and my V here. It's a different case. But the horizontal component was initially, what was it? Looking at the, it's this one, 2V, right? It was 2V. 2V, oh, that was vertical. Oh, I swapped the thing here. The horizontal, oh, it's right. Okay, the horizontal component is 2V, yeah. So 2V, because we already know that V is 6, so the horizontal component is 12. Okay? Yeah? So V is just, what? 12 over sine 60, and that is going to be 12 over 3 over root 2. That's just going to be 24 over root 3. I mean, we can keep it like that because, again, we're gonna use energy here. This will be the resultant speed. It's the speed of the particle at this point. You don't need to find the vertical now. I just found like the like the speed in this direction. Yeah. So again, KE lost equals GPE gained. Simple. So KE lost 1/2 m. Well, we're going to start from 20 squared there, minus the speed at this point, 24 root 3 over root 3 overall squared like that, equals m, and g is 10, and h is what we want to find. And that's it, just one equation and it's done. Yeah. See, if you use energy and you know how to use it well, it's going to help you a lot. Yeah. So m cancel. So I get 400 here in the brackets. And minus that's 24 squared is it I forgot. Wait, hang on. Or I can do this. Well, let's use a calculator. Over 3, right? Because root 3 squared. So that's 9192 equals 20h. Okay, so h equals 400 minus 192 divided by 20, 10.4. I think that's it. That's the answer there for part B. Oh, 2 significant figures? Well, that's just going to be 10 then. Right? Yeah. Okay, so that's the answer to part B. And that's it, guys, for this whole paper. It's not too bad this year. So my opinion on this paper would be it's going to be easier than the Jan 2025, easier than all the 2024. I'm not sure about the January 2024. Maybe this one is about as easy, but surely the June and the Aug in 2024 are harder than this one. January 2025, I don't think so. This one is also easier. So if you want to compare the grade boundaries or anything, maybe it's not going to be last year, perhaps maybe the year before, 2023, or even the October 2022, because in 2022 there was COVID. So maybe overview of the questions, right? This question is I think at least it's carefully designed, although it's easy, but it's carefully designed because if you look at the numbers here, they're all nice. And the nice thing about this paper is that they try guide you step by step, right? If you look at the first question here, yeah, so they tell you what you expect. Like they almost, like, I think 50% of the questions tell you what you should get. Like show that, show that, show that, like you see continually here in this paper. like the first question, you see more than 50% here, right? Again, the tricky part here in the first one should be part C. You just have to use a little bit of logic to make it easier. In math, if you know how to incorporate logical thinking when solving a problem, it is usually gonna make the problem easier to solve. Trust me, I've witnessed this, right? And for those people who don't like to use logic that much, they're gonna struggle solving a problem, right? So you use logic to simplify the problem, basically. Yeah, so that was number one. Number two here, basically, because impulse involves change in momentum, hence change in velocity. So you probably have to find the velocity first, and because they give you a position vector, if you differentiate that, you get velocity vector. So that's just the key part there to know, right? And the rest should be fine. This part, I think the only tricky part is B, because they ask you to solve for tan theta, and it's not the usual angle between the vertical, would have been the vertical OA here, and the downward vertical when suspended freely from A. But it's the angle between AE and the downward vertical. So there are questions like this from the past papers. You just have to watch out for it. And yeah, usually you could try use sine or cosine rule, but in this case it asks you to solve for tan theta and not theta. I mean, if it did ask for theta, I don't think it would have asked for exact value there. So because it specifically asked for tan theta, so it wants exact value, and we can only do that by using the additional formula for tan A minus B. All right. And in other questions, it might ask for cos or sine. You just have to know, right? Just have to experience on this. Yeah. Number 4, I think, well, yeah, it's not that bad. It's just force equilibrium, because you know that it's a constant speed. You have to know that it's equilibrium there when it moves at a constant speed, and now at an acceleration. So the force from the engine, like F equals P over V there, can change depending on the speed. Yeah. So when you go uphill, right, you want to use a low gear. I mean, if for those of you who know how to drive, or maybe experience how driving is like uphill or downhill. So when you go uphill, you need low gear, because when you use low gear with the same power of the car, you can generate a lot of force. And in the technical term, more relevant to the car there is torque, right? So more force means more torque, and then it's going to make you climb up the hill more easily. So when you go uphill, you use low gear. When you go on like street or roads, you use high gear, right? Because we want more speed, so we use high gear there. All right. And that's it for this one. Well, yeah, work and energy principle. I mean, it doesn't have to tell you. Usually, a harder paper won't tell you to use work and energy principle here. You need to know, right? So my bottom line suggestion here for M2, look for energy conservation. Not just watch out for it, but look for it, right? Like, look if you can implement energy conservation. It's going to help you a lot. It's going to help you a lot, right? Just look for it, yeah? In this case, you can, because you have speed, kinetic energy, and GPE, gravitational, from the height there. So there you go. Number 5. Yeah, this one in other years, I walked through like 3 years already on M2 as of the time of recording. And I found that this question usually took my marks away, right? They were tricky because this is easy. This is relatively easy. Usually, a hard paper would have come with like consecutive collisions. So PQ would have collided once and again later. So the Q would hit the wall and bounces back, colliding P again for the second collision, and they might ask for even like the final speeds after that second collision. That is what a hard paper would have looked like in this one. Yeah, so maybe try look for the previous years if you want to get more and more proficient on this one. But the trick here in part D is just, you know, when they give you the coefficient of restitution between the wall, you just multiply the speed before hitting the wall by that coefficient, and it's gonna be the speed after hitting the wall, right? Straight. And again, this is nice because they tell you what you should get along the way as well, so that should be fine. Yeah, this one again, I already gave you the advice. There are 3 questions, so there are 3 kind of like separate equations: moment, vertical force, horizontal force, leading to these 3 questions. Usually it is like that. That's just my general advice for static equilibrium. It's similar in M1, it's similar again in M2, just like that. The rest is just math, but the physics in this question is just these 3 equations here. Yeah, static equilibrium. All right. Yep, 7 again. Well, this one, yeah, they didn't tell you if you should use energy or not, but sorry, they did tell you in the first part, but they didn't tell you in the second part, part B, and that is a good example. They could have not told you here in part A, and still again. So let's see, if this paper was designed to be harder, then, you know, none of the 2 questions would tell you to use energy. But you have to realize that energy works here. And energy is like the key quantity in physics, right? So you think about energy more and more, it makes it easier. Yeah, just trust me there. Okay, so this one is fine. Part A, they tell you what you should expect. Part B, yep, using energy again, exactly the same approach in part A, but you just solve for a different variable. So this should be easy if you use energy. If you use kinematics, yeah, I guess you probably might need to find alpha as well. I don't know, but I don't want to try that because I always go for easier way, and you guys should too. But maybe you guys can try using kinematics and solve if you realize that, okay, you should use energy, right? Okay, so that's it for this whole paper. I hope that was all useful. If you find the video useful indeed, you should subscribe because I'm gonna walk through more and more of these papers, and do check out other papers that I already walked through, and stay tuned. I'll see you in the next one. Bye.